In this video, we'll be reviewing Chapter 5, which is probability, which is, I think, some people's least favorite topic, but it is a very important topic. It will for sure be a good percentage on your AP test, and now that it's so shortened, it'll for sure be on one of the free responses. So let's spend some time going over these main points and formulas, and hopefully it kind of simplifies this probability chapter. So the first thing we talked about in Chapter 5 was doing a simulation, which is just an imitation of chance behavior to help you predict some outcome. And this kind of goes back into how we did random, how we talked about how would you randomize something. But when you do a simulation, you need to make sure that the chance of something happening is staying the same, right? So you want to make sure you're keeping whatever you assign. You want to make sure that probability of it happening is staying the same. So normally, if you have to write this out on a free response, you would do some type of sentence as use, and then you say what numbers you're going to use for your simulation. So it just kind of depends on your problem, but you have to make sure the digits line up, right? So this is just an example, but these could be any. If you're going to use 20 numbers, you would want this to be 0, 1, so that it has 2 digits. And you could say use 0, 1 to 20, and that's 2 digits. If this went up to 3 digits, then you would want to do 0, 0, 1 to 100, or whatever you're doing for blank. And you could say 21 to, I don't know, let's say 50 for blank. And you would just make sure, so you want that to be a 20% chance, that to be a 30% chance. And actually, you know what? No, because I didn't go to 100. So ignore what I just said. But you would want to make sure the probability is equivalent. When we do an example, hopefully it'll make more sense. And then, so you assign your numbers. That's what I was ultimately trying to say there. And then you have to say, and ignore. So you first assign. Then you say, what are you ignoring? So if you notice, we started at 0, 1, so you would need to ignore 0, 0, and 51 to 99. Any other 2-digit combination. So you say what you're assigning, you say what you're ignoring, and then you're going to say stop and keep going until you reach whatever your scenario is talking about, and then you'll say stop when blank, and then you just record whatever, how many times you got this. Or I don't think this is probably making much sense, but again, maybe when we do an example. I was just trying to give you like a format for what the sentence would look like, but without an example it was kind of arbitrary. Also, you could look back in your Chapter 5 notes, and that might help clear that up if that didn't make sense. For do, you want to perform many repetitions of the simulation. So this is just one repetition. When you stop and you record whatever results, then you want to do it again. So, the more repetitions, the better. If this was a free response and you're actually doing it and not just planning, they would probably tell you, do 3 repetitions or whatever. Okay, so for probability, we should know it's always a value between 0 and 1, so you should never get 1 point something. And this is the notation we use. Probability of A is just the number of times A occurs divided by the total. We know that. The complement rule is if you know the probability of A, then 1 minus A, which gives you the probability of, that means like not A, the opposite of A. Because it either is one or the other. It's either A or not A. So, like the complement of A stands for not A. So, like if you knew the probability of being a girl at Waco High, then 1 minus the probability of being a girl will get you the probability of being not a girl. So, then, because sometimes that's going to help you if you're looking for the opposite. Keep that in mind. It might make your problem simpler. So I'm going to skip over mutually exclusive. I think what we're going to first do is this formula that's on your formula chart. These are your two probability formulas on the new formula chart. They're the same ones, but so the probability of A, this sign stands for OR when it's a U. A, it's a union, A and B. Sorry, I just said and. The probability of A or B would be the probability of A plus the probability of B, and then you have to subtract the probability of A and B, the intersection. So that is this formula where they put right there just in words. So OR would be the U, and the AND would be the upside down U. And so why is that? If you use a Venn diagram to think about this. So if you have, this is A, this is B, and they overlap. So if they overlap, that means they're not mutually exclusive. You can be both. If you can be both, then you got to think about it. If we were going to find the probability of A or B, well, the probability of A would be this whole circle. The probability of B would be this whole circle. So then you need to subtract that union, the overlap, because you double counted it. These people that fell in both, you counted them in A and B. So you need to subtract that section so you don't double count that. That's the idea behind the formula. But if they are mutually exclusive, so if your Venn diagram didn't cross, they had no overlap. That's supposed to be a B. I put like too many indentions. Now I'm making it worse. There we go. Then we don't have to worry about subtracting the overlap because that's going to be 0 regardless. The probability of A and B would be 0. So you can always use this formula, but it kind of helps to know if they're mutually exclusive. If you can't be both, then you can just add the probabilities. So remember, I always tell y'all, associate OR with addition and with multiplication, because if you don't know how to use these formulas, it's going to simplify it a lot for you. So then our next formula is the conditional probability formula. So the probability of A that's given B, if they give you some type of information, then use this formula. And so if you want to write, this symbol means given. And again, the AND would be an upside down U. And you could switch the order, right? So the way I read it is the probability of something given some information is the probability of both over the probability of the given. Given needs to be on bottom. So it doesn't matter A or B, it's that letter that was second needs to be on the bottom. So if they give you conditional probability, yes, you're going to use those formulas, but also a lot of times if you don't know where to start and it just seems like percentages and you don't know what to do with it, do a tree diagram. Especially on a free response, I bet you if it's a probability question, it's going to help to do a tree diagram. It probably wouldn't hurt, so you might as well try it. So here's an example. So a survey was done and found that 93% of teenagers use the internet, 55% of online teens, so out of those ones that use the internet, have posted a profile on a social networking site. Find the probability that a randomly selected teen uses the internet and does not have a social networking site. So if you start your tree diagram, and the first thing they're talking about is the probability of just using the internet. So you write your two different outcomes, and it could be more than two. You have as many branches as they talk about, but in this case, they either use the internet or they don't use internet. So what's the probability of using the internet is 0.93. Always change it to decimals. So then what does that make this probability? It has to be this or this. So it's the complement, right? It's what we talked about up here. It'd be 1 minus 0.93, which is 0.07. Okay, so then from there, after that, we know if they use the internet or not. We know if they use the internet, if they're online, then the probability of posting a profile on a social networking site is 0.55. So I'm just going to abbreviate this. Uses social media, SM, or does not post a profile, does not use SM. And so the probability of using social media if it's given that they're online is 0.55. That makes this one minus 0.55, so 0.45. So normally then they give you some information for if they don't use the internet, but you got to kind of think about this one. What's the probability of using social media if you don't use the internet? Right? That's impossible. 0.0, or just 0. You don't even do 0.0. There is no chance they're using social media if they don't use the internet. Then that makes the probability of not using the internet, or the probability of not using social media, given that they don't use the internet, 1. Because it would have to add up to 1. So then what does all this help us do is now as you go through your tree diagram, you multiply through the branches. So to get this final result, this would be the probability of using social media given they use the internet would be, and you would just multiply through, oh wait, no, what am I thinking? Not given. Dang it, I hate messing up in these videos. Cross that off. I don't know why I said that. This is the probability of using the internet and using social media at the end. So the probability of using internet and social media would equal 0.93 times 0.55. So then you multiply those together, which I don't have that in front of me. 0.93 times 0.55 is 0.5115. This would be the probability of using internet and not using social media, and you multiply through, so 0.93 times 0.45 would be 0.4185. And then down here, the probability of not using internet and using social media would be 0.07 times 0, which is 0, right, because it's impossible to do that. And then the last one, the probability of not using internet and not using social media is 0.07 times 1, which is 0.07. So now we have all these probabilities, but what did it ask for? Find the probability that a randomly selected team uses the internet and does not use social networking. Well, that is this one right here, so that is your answer, 0.4185. So you didn't have to write all this out. I was just trying to show you the breakdown, even though I majorly messed up. And sometimes they take it a step further, so they say, well, what's the probability of using the internet? Or what's the probability of not using social media? Well, the probability of not using social media is this outcome or this outcome. So you would add all your not using social media probabilities, so you would add these two. So just keep that in mind also. I hate that I did that though, because that's a major mess up. What is that conditional probability? It was this one already. These branch probabilities are conditional. Okay, so then the next idea is two events being independent. So what's the idea behind independence is, does knowing one help you know the probability of the other, right? So if they're independent, if I know B, it doesn't change the probability of A. The probability of A, right? Given B is just equivalent to the original probability of A. And flip-flop, given A, it doesn't help me know the probability of B. It's still just whatever that original probability of was. So the way I think about it is, given 1 doesn't change probability of other. And now this little thing you're supposed to prove, if it asks on a free response, are they independent, you show this. And if these two statements are true, then you say they're independent. If one of these is false, then you would say they're not independent or dependent. This is not on your formula chart, okay? So this is just a fact you got to memorize. So if you know that two things are independent, whether it says it or you prove this or it's common knowledge that knowing one wouldn't change the probability of the other, like flipping a coin and rolling a dice, right? We know that the coin has no effect on the probability of the dice. So if they are independent, then the probability of A and B, you can just multiply them. The probability of A times the probability of B. So remember that this would be the probability of A, and is the intersection upside down mu, would just equal the probability of A times the probability of B. That's why I say and is multiplication. Now if they weren't independent, it would be a little bit more complicated. You would have to manipulate this formula to get probability of A and B alone, so you'd multiply by probability of B, but I wouldn't worry about that, honestly. If you just remember this fact, it's probably going to work out to where they're independent. And then the last thing is, if they're mutually exclusive and independent, or that can't happen, right? So if you're mutually exclusive, you cannot be independent, because if one event happens, then the other event's guaranteed not to happen, which would mean it changes the probability, right? So, for example, if let's use a Venn diagram, right? So if you're mutually exclusive, you don't overlap. So the probability of A given B, let's say the probability of A is 0.4 and the probability of B is 0.5. Well, if it's given that you're in B, well then what's the probability of being in A? 0. It's impossible. If it's given that it's in B, it can't be A because it's mutually exclusive, so that's 0, which doesn't equal that probability of A originally, which is 0.4. So they are not independent. So if you're mutually exclusive, given one's going to change the probability to be 0, and it's not going to be independent. So I hope that made sense. If it didn't, just know they can't be both. And an example is being male and being pregnant, right? Given that someone's pregnant, it's going to be pretty obvious that the probability of being male is 0. So that is an overview of Chapter 5. The main things I want to highlight are the two formulas from the formula chart. Go back to those if you get stuck in using a tree diagram. And again, you probably hear my dog whining because he gets needy every single time I do a video. Next, we will cover Chapter 6.